welcome to the topic on preparing for multivariate analysis. Today's statistical software packages are great because they allow us to be very efficient. No longer are people calculating analyses by hand, or at least they certainly don't have to. So now we have these point and click software programs like SPSS, which can be great in that you can point and click, but they can also be horrible in that you can point and click, because we can do things without really understanding why we're doing them, or whether what we're doing makes sense, whether we've selected the right analysis, whether we've selected the right variable. So we need to talk a little bit about kind of like the fundamentals of research. One of the great things about this job, I guess maybe not if you're an extrovert, but if you're more introverted like me, one of the great things is you can just sit alone and think about not just the analysis that you're going to do, but you can think about research questions and how you're going to address them, the data that you would need to collect, who you would need to collect the data on, the types of measures that you would use. So that's kind of the fantasy of research. What we would ideally do. In an ideal world, we would begin this process. And the, I guess, reality is that with a lot of research now, it's based on secondary data analysis. So instead of collecting data ourselves, we're given a data set and we're told we need to figure out a research question. And that's what I'm asking you to do in this class. We don't have the time for you to go out, collect data, develop a research question. We're just telling you to go find a data set, secondary data, and mine it to address some research questions. And so in some ways, it's not the best way to do things, but we're constrained by time. But we can at least begin to understand part of the process of research, which is making sure that we are using the right test, the right statistical analysis for the question that we have. And this requires doing something that SPSS cannot do for us, or at least we need to tell SPSS to do it for us, which is understanding the structure of our data. So we need to know whether our variables are nominal or ordinal or interval. We need to understand the distribution of these interval level variables. And then we can begin to come up with a research question of interest. I would say that the number one mistake that I see grad students make when they want to do quantitative analyses is that they decide what they want their research question to be, and then they use data to address that research question. The reason why this is a mistake is because very often students aren't going out and collecting their own data, or they're relying on collecting data on an existing study. And so you don't actually get to collect data for the specific purpose of that research question. And so students get these great ideas, but they're not feasible. What you have to do in this class is understand your data first and then create the research question. So that's kind of the backwards process. The ideal process of research question development is you think about theory, you think about gaps in the literature, and then you can begin to collect your own data to answer those research questions and address those gaps. You can't do that here. You need to think about what are the data that you actually have and what is an important research question that you can address based on these data. It comes down to a question of moving from concepts to operations, from conceptualization to operationalization. Can we find measures in our data that appropriately capture theoretical constructs of interest? If you're interested in psychopathy, you can't just go and decide that this one item is going to be your measure of psychopathy. You have to begin to ask, okay, so does this data set actually appropriately measure psychopathy? What are the strengths of this data set? What are the data in this data set that I can actually use? So I want you to take the time to think about not just developing a research question. Know your data first, and then develop the research question that you might be addressing for your term paper project. So I think this is the most accurate cartoon that I've ever seen about doing research. And it's the point that I've kind of alluded to in the earlier slide, which is we can't fit square pegs into round holes. We cannot force our data to be something that it's not. So that's why you need to understand your data first, or else you're going to waste your time. You can spend all the time in the world thinking about the greatest research question that has ever been asked. But if you don't have the data to do it, then all that time has been wasted. Now, it wouldn't be wasted if you're sitting in a tenure track position, or you're a research faculty member and it's your job to think about this over the span of your entire career. But in 4 months, 3.5 months, however long the semester is, you don't have the luxury of time. You don't have the luxury of sitting down, thinking hard about the key gaps in the literature, how you're going to address those gaps, how you're going to design your study, pass research ethics, and so on. You need to know your data and then formulate a research question. Most importantly, I cannot stress this enough. This is a class that is evaluating your ability to demonstrate an understanding of the analyses that you're doing and an interpretation of those analyses. This is not a class that assigns a grade based on your ability to find something as significant or meaningful, a large effect size, what have you. It's not your job to find something statistically significant for your term paper or for your assignment. Your job is to run the analysis in the right way, understand why you're running the analysis, and interpret that analysis correctly. I'm forcing you to do particular types of analyses. I'm telling you to do a logistic regression analysis. Maybe your research question or your data are not ideal for logistic regression, so I'm not going to criticize somebody for not finding a significant relationship. What I'm looking for is an understanding of why you're doing the test, how to do the test, and then how to interpret the results of that test. So I'm going to begin the content for this video by describing univariate analyses, which is literally just describing a single variable. No statistical significance test, no effect size test, just understanding the distribution of your data. Then we'll talk a little bit about classic analyses, which we'll refer to as null hypothesis significance testing, or NHST. But there are some scholars that want to move away from null hypothesis significance testing and focus instead on effect sizes. So when we're looking at these NHST tests, we'll describe 4 different types of bivariate analyses. Chi-square test, so it's chi, not chi, like your chai tea or anything like that. Different types of t-tests, ANOVA, and correlation analyses. Some of these are parametric tests, others are non-parametric tests. A parametric test is essentially saying that we are assuming that the data that we are using are normally distributed, especially our dependent variable is normally distributed. A non-parametric test does not make an assumption about the distribution of the data. So the big question that we should be thinking about, especially as we move forward when we're thinking about what our journal article is going to expect of researchers in the future, is an attention to effect sizes. What we'll find is that if you are doing null hypothesis significance testing, you would expect that about 1 out of every 20 analyses that you perform will be significant based on chance alone. We'll also find that if you have a large enough data set, you can, at the bivariate level, literally find like almost anything to be significant. Very minuscule differences can still be significant. So do not think about significance as importance. Significance is more a statistical description, not an indicator of the magnitude or the degree of an importance of a finding. That's where effect sizes come in. Effect sizes tell us how strong the statistical association is, or how strong the statistical difference is. So let's start with univariate analyses and describing our data. Now don't worry, for our asynchronous component in week 2, I will also talk about how to describe our data. So I'll open up SPSS and show you some different ways of doing things. The reason why univariate data analysis is so important is, again, like, you need to learn how to walk before you run. My goal in this class is for students to develop skills and fundamental understandings. This is not advanced quant. This is the introduction to quant at the grad level. we need to make sure that everybody understands why these multivariate analyses have particular types of assumptions or requirements. And to understand these assumptions and requirements, we need to understand our variables. We need to understand the distribution of our data so we know whether we're selecting a parametric test or a non-parametric test. So the distribution of the variable that we're looking at dictates the type of analysis that we're going to perform. Simply running descriptive statistics through SPSS can provide us information, but then we need to interpret this information. The first half of this lecture is going to focus on understanding the principles of core bivariate analyses, and then the back half will look at addressing some of the assumptions and dealing with the realities of criminological data. Very often we're going to violate certain assumptions. What you are needing to do as a student in this class is simply show me that you understand that you have maybe violated an assumption. Sometimes there is nothing that we can do about the violation of an assumption, especially when I am requiring you to run a specific type of analysis. Your job is to, in your assignment or in your term paper, acknowledge to me that you've understood that you've violated an assumption and explain to me what you've done or tried to do to address the violation of this assumption. And if you could not address the violation of this assumption, what might the implications be for the interpretation of your own analysis? Describing your data isn't just for you, it's for your reader. You want to tell your reader a story. You want your reader to get a sense of who is in your sample. What are the people in your sample like? If you just skip to multivariate analysis, you gloss over these key details that kind of help frame your paper, help give context to your paper and who your sample actually is. So when we're thinking about levels of measurement and describing our data, a nominal variable is a categorical variable. So maybe we want to describe the different characteristics of something without ranking that thing. So we could take beer as an example. We have different types of beer. Maybe we're looking at a stout or a pilsner or an IPA. These are different categorical descriptions, but we can't, unless you're some like snobby beer drinker, we can't rank those. We don't know whether an IPA is a better beer than a pilsner. It is. Ordinal level variables can give us some indication of the rank order of particular beers. So maybe we can rank beers in terms of different characteristics on a what we traditionally refer to as like a Likert-based scale. So we could talk about whether on a scale from 1 to 5 we would strongly disagree or strongly agree that the beer is hoppy, or we would strongly disagree or strongly agree that the beer is light. An interval level variable would be describing maybe the alcohol content of a beer, where we can know both the rank of the alcohol volume, but also the magnitude of difference between alcohol volumes. An ordinal level variable can tell us about rank, but it cannot tell us about degree of difference. We don't know the numerical value of the difference between strongly disagree and disagree. With something like alcohol volume, alcohol percent, we know both the rank order and the degree of difference. A 4% beer is 2% less than a 6% beer. So that would be an example of an interval level variable, when we actually know the degree of difference in the unit of measurement. In the graph here you can see it's referring to a metric variable. It would just be another name for an interval level variable. A dichotomous variable is just a special case of a categorical variable, specifically a nominal variable. But a nominal variable need not be confined to just 2 categories. We could have a nominal variable of countries and we could have 150 countries. It would be a very inefficient variable, but that would technically be a nominal variable. So this slide is more so just for you to understand the difference between these different types of variables. So the difference between an interval level variable and a ratio level variable, which I haven't really talked about, is that a ratio level variable has a natural 0 point. So the 0 is a naturally occurring value. For the purposes of this class, I'll probably just end up using interval level variables and ratio level variables interchangeably. What we mean by an exhaustive category, and it's a quality, it should be a quality of all of our variables, is that when we say asked a participant a particular question, the question captured all possibilities. So let's take a very simple example. Let's say that I was interviewing students in this class and I asked them what their nationality was, and I included Canada and the United States. Well, I know we might have some students that are not from either of those two countries, or maybe they have dual citizenship, so they define themselves as both Canadian and American. So in this case, we failed to have exhaustive categories. Maybe somebody is from Nigeria, or from China, or from England. In this example, we might have also failed to create mutually exclusive categories, because somebody could be both American and Canadian if they hold dual citizenship. So unless I had an option box that said Canadian and American, we would not have our categories as being mutually exclusive. A person could select into multiple categories. That rank order is characteristic of ordinal, interval, and ratio level data, but not nominal level data. Nominal level data doesn't tell us whether Canada is better than America or scores higher or lower than America on anything. It's just a descriptive measure. Ordinal level variables, again, don't tell us the degree of distance between two indicators on a particular variable. So here's where students can get confused. I could sometimes administer a scale where I'd ask somebody, do you agree that this beer tastes good? I give someone a beer and then they could do strongly disagree as 1, disagree as 2, neutral as 3, agree is 4, strongly agree is 5. So a student might say, well, yeah, we do have a interval level variable here because I know that 3 is 1 greater than 2 and 1 less than 4. But that's not what we're measuring. We're using these 1, 2, 3, 4, 5 categories to simply reflect or indicate what these different qualitative descriptors are. So we know that neutral is less than agree, but we can't say that neutral is 1 point less than agree. We don't know the magnitude of the difference between neutral and agree, or agree and disagree, and so on. So we don't have that measure of distance. Here's where we can get creative or bend the rules a little bit. As a general idea, if we have a ordinal level variable with, let's say, like 5 or 7, I tend to put like 7 different categories. So a degree of agreeability from 1 to 7. For the purposes of this class, I'll allow you to treat that as an interval level variable because it is capturing a bit of a wider range. So technically, we don't necessarily know the magnitude of the 1 versus 2 or the 2 versus 3. But we can, for the purposes of this class, for the purposes of you needing an interval level variable, you can use that variable in your own analysis. But before you do that, what I recommend doing is thinking about, can you create your own interval level variable? Very often, when we're measuring these Likert scale variables, our intention is actually to use them to create a larger scale. So for example, my background is often in assessing for features of psychopathy and measuring psychopathy. And I'll use the comprehensive assessment of psychopathic personality. And I'll be rating an individual on their level of manipulativeness, their level of self-entitledness, their level of having a lack of remorse, detachment from others. So I'll rate these individual features of psychopathy on a scale from 1 to 6 or 0 to 6. And I can sum all of these together to create a much bigger scale. So the CAP ends up being out of 132, 133 points. What that means is I can then use that scale as a measure of an interval level variable. When we have nominal or ordinal level variables, we want to make sure that we're describing them to our reader in the right way. If you have a dichotomous indicator of whether a person recidivated or not. So it could be yes or no. And let's say you scored no recidivism as 1 and yes recidivism as 2. If you ran a description of this variable as an interval level variable and 50% of your sample recidivated, the mean value on this variable would be 1.5. That's not actually really telling us any useful information. We're not interested in the mean score of recidivism in the sample. We're more likely to be interested in, okay, what percent of the sample recidivated and what percent of the sample did not. So we'd want to describe the sample size and the percent. So let's say we had a sample of 500 formerly incarcerated individuals, and we wanted to see what percent of them recidivated after a 2-year follow-up. 250 of them recidivated, meaning 250 did not. Always presenting the percentage first, because that gives more context to the readers. So when it comes to dichotomous variables and nominal variables, always describe them in terms of percentages or n's. Sometimes it can be more appropriate to treat an ordinal level variable as an interval level variable and describing the mean and the standard deviation of that ordinal variable. It's really only appropriate when you have an ordinal level variable with a wide range, so that's on a large scale of like 1 to 7. Now we'll take a look at interval or ratio level variables. So an example of an interval level variable could be age, or the duration of somebody's criminal career, the number of days that they've been incarcerated, and so on. And what we're interested in when we look at the univariate description of interval level variables is whether they are normally distributed. The reason why we're interested in the normal distribution is because many of the assumptions associated with our bivariate and multivariate analyses are based on the variable of interest being normally distributed. So the middle of the graph there shows a normally distributed variable. This is when the mean of the variable, so the average level of the variable, the median of the variable, so what is the score on this variable when we look at the very middle of the distribution, and the mode of the variable, meaning the most commonly observed value of that interval level variable, are all the same. The mean, median, and mode, okay, they all need to look about the same. So how do we calculate this? So mean, very easy to calculate, just looking at the average age within a sample. Let's say we have high school students and 500 high school students, and the mean age is 16. We would then, to calculate the median, need to put all of the ages of those 500 students in rank order, whether it's lowest to highest or highest to lowest age, doesn't matter. We would then look at that 250th person in that sample. What is their age? If it's a normal distribution, we would expect their age to be 16. For the mode, how many students are age 12? How many students are age 13? If we have 251 students of the 500 that are age 16, then we know that 50% of this sample is age 16, meaning that the modal value for the sample would be 16 as well. When we have negatively skewed data, what this means is that the mean is less than the median or the mode. When we have positively skewed data, it means that the direction is going towards the right side of the axis, the tail of the distribution is going to the right side of the axis, and the mean is further towards the tail end of the distribution than the mode or median. If we're looking at the distribution of offending amongst people that we know to be involved in crime, we're typically going to see positive skew. So think about the age crime curve. I've got my desk here that's built off the age crime curve. The age crime curve is positively skewed. Same thing if we're looking at something like income. That's why, or housing prices. That's why when we're looking at housing prices in Vancouver, the media often reports the median cost of housing, because the mean cost, there can't be a zero cost to a house unless we're looking at money laundering or something like that. Now for a discussion of how we would actually calculate the distribution of interval level variables. There are different ways to report on the distribution of interval level variables. One way is to report the range, which would be to describe the minimum value and the maximum value. So what is the youngest person in the sample and what is the oldest person in the sample? So this can help us identify outliers, which would be scores that we would not expect. So if we've got a high school sample and somebody is 75 years old, then we would have to be like, okay, let's take a closer look at this participant. Were they actually 75 and just eager to go back to school? Or was it a data entry mistake and someone was supposed to enter 15 but they entered 75? Or did some punk ass kid just write 75 on their survey because they wanted to be a punk ass kid? These are the types of things that are going to happen when we do social science research. Our variance tells us the spread of the data, which is the average of the sum of squared differences from the mean. So let's take a very simple example. Let's say I was asking students to rank me on this lecture. People were so bored of the lecture that most people didn't even get to this point, so we only have a sample of 4. And on a scale of 1 to 5, I received a mean score of 2, indicating poor performance. And the distribution of scores was as follows. We had one person giving me a 1, another a 3, another a 1, and another a 3. So our variance is just calculating how far each person's score varies from the mean. So we would take a person's score of 3 and minus it by 2, aka the mean, and we would do this for each individual value. What we need to also do is square that value. So if we do 3 minus 2, that's 1. And if we do 3 minus 2 again, that's another 1. A 1 minus 2 is negative 1. A 1 minus 2 is negative 1. And then if we were to sum up all of those, we would actually get a value of 0. We square these values so that we have a non-negative number. So 3 minus 2 squared is 1. 3 minus 2 squared, 1. 1 minus 2 squared becomes 1. 1 minus 2 squared becomes 1. So our total sum of those values is now 4. And we divide that by n minus 1. So you can see in that formula there, n minus 1. And that is the routine procedure that we use to calculate degrees of freedom. So 4 minus 1 equals 3. Our numerator is 4. 4 divided by 3 equals 1.33. So that gives us our variance value. Our variance is 1.33. Big question that students will have. Okay, how many formulas do I need to know in this class? When you read Garson, he'll throw a lot of formulas at you. When you read the Green books, you'll get even more formulas. Formulas that I want you to know about are the ones that you're going to see in my lecture slides. What do I mean by degrees of freedom? Like if you've played Sudoku, this is really cool. I love how simple degrees of freedom is when you actually begin to think about it and understand it. If I know that the mean score for the sample is 2, if the first 3 values are 1, 3, and 1, there's only one possible value that the 4th score could be. To get a mean of 2, the 4th score must be 3. So for our 4 values, the first 3 could theoretically take any form. They're free to vary. But once we know those first 3 values, we know that the 4th value it's not free to vary. It is constrained to be one specific thing. And this isn't just true of n equals 4, it's true of n equals 617. It doesn't matter. The idea is that once we know n minus 1 values, so 615 values, we know what the 616th value must be if we know the mean, which we do. So that's why we do n minus 1 to figure out the degrees of freedom. The standard deviation is so simple once you know how to calculate variance. If we look back to our previous slide, we can see that variance, which is just that s squared, equals sigma, which means the sum of x, which means our individual value in the sample, minus the mean value in the sample, squared, divided by n minus 1. That gives us our variance value. All we have to do to calculate the standard deviation is just add a square root across the variance equation. what this does is returns our original unit of measurement. We had squared our values, and that will elevate or inflate how different our scores are. What we can do here is just square root everything to get us back to our original unit of measurement. So if we square one side of the equation, the square root is just the inverse of squaring something. So 2 squared is 4. The square root of 4 is 2. So now we're back to our original unit of measurement. So if we take the square root of 1.33, we would get 1.15, which would give us our standard deviation. What does the standard deviation even mean? We'll start with kind of the answer, and then I'll explain how we get these values. So in short, what the standard deviation means is that 68% of all observations in our sample would be plus or minus 1.15 units away from the mean. We can also say that 95% of cases would be 2 standard deviations above or below the mean. We would look at an x-axis, our mean point right in the middle, and we could look at 1 standard deviation to the left and 1 standard deviation to the right, and that would give us 68% of all observations or all values that would occur in the sample. If we looked 1 more standard deviation to the left and to the right, we would get 95% of all sample members captured within these 2 standard deviations. So how can I say that? Where am I getting this 68% number from? Where am I getting this 95% number from? Let's take a closer look. Here's a nice, beautiful normal distribution that takes the shape of a bell curve. And all bell curves, all variables that look like this normal distribution, have the exact same qualities. So keep in mind, the normal distribution is something we artificially create. Every single normal distribution takes the same properties. The properties are as follows. That 0 value that we see right in the dead center of the normal distribution, that represents our mean value. Think about it this way. Remember when we were doing x, which is any given value, minus the mean? If we had x as our mean value, let's say our mean was 2, 2 minus 2 equals 0. So that's why the mean is always referenced as 0. If we look minus 1 standard deviations away from 0, we get 34.1% of all cases under the normal distribution. If we look 1 standard deviation above the mean, another 34.1%, and with rounding it actually works to 68.3%. So that's where I was getting those numbers before. 68.3% of all cases will fall between -1 and 1 standard deviations from the mean. If we branched out further and look at 2 standard deviations below or above the mean, we would get 95% of the sample. So effectively what it's showing that if and only if, so IFF means if and only if and only if the variable follows the normal distribution, then we can really accurately describe the nature of individuals in the sample, the nature of the distribution. So if someone told me that this variable, let's say its IQ, was perfectly normally distributed and the mean was 100 and the standard deviation was, let's say, 15, I would know that 68.3% of the sample would score between 85 and 115 on this IQ test. So let's take a look at how we put this into practice using null hypothesis significance testing. So you can see in the graph here, it's again showing that traditional bell curve is perfectly normally distributed. We know that 2 standard deviations above the mean and 2 standard deviations below the mean are quite unlikely. 95% of all cases fall within 2 standard deviations above or below. So things that occur outside of this distribution is particularly rare. Now here's where students can get confused. Where the confusion can arise is thinking that, okay, if a value lies outside of 2 standard deviations, then it's significant. That's not what we're talking about here. What we're talking about here for NHST is the p-value, is the probability that we observed these differences actually unlikely to occur in the general population. So our alpha value is typically set at 0.05. So let's take some time with this to unpack this, because null hypothesis significance testing is talked about so often that it sometimes can create even more confusion. So essentially what we're asking is, what is the probability that when we would get a value that's greater than or equal to x when sampling from a population where the true value equals 0? That doesn't sound very helpful at all. So let's break this down a little bit. X just means any value, so let's let it equal 1. So our question is, what is the probability that we would get a value of 1 or more when sampling from a population when the true value is actually 0? This will tell us the probability that we are observing something basically just based on chance. Generally speaking, it depends on the type of analysis you're conducting, but the null hypothesis would say that there is no relationship or no difference between the variables being considered. When we reject the null, we're saying that our null hypothesis significance test is significant. Null hypothesis significance testing is really only appropriate for analyses of a sample rather than an entire population. Because if we have the entire population, then we have the true value. So it makes no sense to be talking about whether our value x is different from the population when we actually have a population. It's also not necessarily appropriate for non-random samples, but this assumption is a little more flexible. Very often we have non-random samples, but we do null hypothesis testing anyways. It's just something to mention in a limitations section. So that's what I mean by like the notion of practice versus reality, is that when we have non-random samples, we'll still do null hypothesis significance testing. Let's go back, and I mentioned the alpha level of 0.05. It's a common convention used in science so that we have confidence in the results, but why 0.05? Some people will say things like 0.10 is approaching significance or marginally significant. I do not recommend this at all, and I'll show you a slide in a bit for why I do not recommend this. But I want to go back to something that I said at the beginning of the lecture. Remember when I said that 1 in 20 analyses that you do will be significant based on chance alone? What is 1 divided by 20? It's 5%, or a probability of 0.05. The chances of type 1 error are what we're trying to minimize here. Type 1 error is a false positive. It means accepting the research hypothesis when the null is actually true. So we really want to avoid false positives. To do so, we make it extremely likely that we will not have type 1 error. So if we're significant at less than 0.05, it means that we have less than a 5% chance of making a type 1 error. And again, what we're talking about here when we're doing null hypothesis significance testing is that when we have a value of p less than 0.05, it means that the probability that we would observe the same or a stronger relationship or difference in a population where the true value was 0. And 0 means a non-relationship or a non-difference. So we have the question, and sometimes you can change in SPSS whether you're conducting a 1 or 2-tailed test. So remember I talked about the tails of a distribution. So let's go back to the distribution slide here, and I'll just sort of talk over it. A 1-tailed test would be where the researcher says that we're only going to look at values at the left side of the tail, so on the negative side of the mean. Or we'll only look at a 1-tailed test on the positive side of the mean, so the right tail. What that means is that when we're looking at the right tail, we're only looking at 2.5% of cases. that are above 2 standard deviations from the mean. When we're looking at the left side, it's the same thing. It's not 5% of cases, it's 2.5% of cases are less than 2 standard deviations from the mean. But our significance test is based on alpha equals 0.05. So what happens is if we're looking at 5% of cases on a one-tailed test, we're actually pulling back and we're looking below 2 standard deviations. What this does is it inflates our risk of false positives. It's much easier to find something significant if we do a one-tailed test, because instead of looking at 2.5% of all cases that are greater than 2 standard deviations from the mean, we're no longer even looking at 2 standard deviations above the mean. So hopefully this is helpful. We can talk about this in the asynchronous component because sometimes it's easier to talk this out. But what I'm trying to say is that when we are looking at a one-tailed test and when we set our threshold of alpha at 0.05, it actually looks at a lower threshold in terms of the magnitude or the degree of difference. So it increases our risk of false positives. If you're on Twitter, I definitely recommend that you follow Robert Apple. I don't actually know if it's Apple or Apple. I've never met him, but he's, I think, one of the stronger criminologists when it comes to quantitative research. And here's what can happen when researchers do one-tailed tests. They get perceived as trying to inflate the chances that they find something as significant. It's an example of what we now refer to as p-hacking. We know that we're more likely to have a journal article accepted if we find a significant result. And so somebody will set their test to be a one-tailed test to increase the chances that their result will be significant. But when people like Robert Apple find this problem, they will call people out on Twitter. And so you want to always be doing things the right way, which means always doing a two-tailed test. We always want to be conservative in our approach. For the next part of the lecture, I'm going to be giving some examples of bivariate analyses, and I'll be using the pathways to desistance study. So in the week 1 lecture, I provided some directions on how to access this data set on ICPSR. So you're free to follow along with me at home during the lecture to see what it is that I'm doing. So I'll start with a very simple example. Let's look at, we have individuals from the pathways to desistance study that self-reported as being either male or female. And we can do it it's not very theoretically interesting, but we could look at whether the age at baseline interview differed between male participants and female participants. Our null hypothesis could be that there's no difference in the age at baseline interview between male and female participants. Then there are 3 possible hypotheses that we could make about age differences, or research hypotheses that we could make. We could say that there's a difference in age at baseline interview between male and female participants. We could also have a research hypothesis saying that males are older than females at the baseline assessment, or we could have a third hypothesis saying that female participants are older than male participants at the baseline assessment. What is the difference between the first research hypothesis and the second and third research hypothesis? The difference is in the nature of the tail of the test. The first research hypothesis, H1, is saying that there's a difference in participant gender with respect to their age at baseline, but it's not saying where this difference comes from. So this is the hypothesis that we want to make. We want to make that two-tailed hypothesis test. So if we go into SPSS, what you can do is if you run a very simple mean comparison, you can go up to analyze means, compare means, enter gender as the independent variable, enter age as the dependent variable. It would tell you that males have an average age of 16.05 and their standard deviation from that age is 1.16. So let's pretend that we know that it's definitely normally distributed. What this would mean is that if we subtract 1.16 from the mean. So it would give us like 14.95 and 17.21 as our range. 68% of all male participants would fall between that age range. We can do the same thing for female participants, just to give us a sense of the spread of the data. So we can report this based on the output given to us by SPSS. We always use the t. I should have mentioned this is a comparison of means, so we're doing an independent samples t-test. And that 1,352, 1,352 is our degrees of freedom. So our t-value with 1,352 degrees of freedom equals 0.70. That's the t statistic. Our p-value, or our alpha value, equals 0.487. So how would we interpret this? If you look at Garson, we would talk about how we have failed to reject the null hypothesis. We don't want to say we accept the null hypothesis because we're not testing whether the null hypothesis was true. We're testing whether the null hypothesis was false, and we failed to find evidence that the null hypothesis was false, aka we failed to reject the null hypothesis. What this t-value of 0.70 is saying is that the probability that we would find a value of t equaling 0.70 or larger in the population when the population value is truly 0 would be 0.487. So it's saying that like 50% of the time that we would sample from a population, we would get this value. That means that we're not anywhere near that 95% threshold that we want, or aka p equals less than 0.05. As a note about style, what you see on the slide here is exactly how I want you to report the t-test. So whenever you have a p-value, you put p in italics equals 0.487. I recommend always writing out the p-value, except when SPSS displays the value as 0.000. This is just a rounding issue. Because we're looking at estimates of a sample from the general population or from the population of interest, we can never know something for sure. That means that our value technically or theoretically can never equal 0, 0, 0. The probability can never be 0. It might be 0.00001. In those cases, I always do p less than 0.001. We'll start with what I think is the simplest analysis, which is a chi-square analysis. And you can get that little chi value if you go into Word. And if you go Insert at the top ribbon on Word, you should find symbols, and then you can insert the chi value there. When we're doing a chi-square analysis, we're looking at whether what we observe is different from what we would expect. So let's just say we were looking at the association between gender, in this case male participants and female participants, and their proclivity for depositing their recycling or putting their recyclables into the garbage, into the litter basket. So our question is there an association between gender and littering, or gender and how we approach recycling? Our sample includes 25 female participants and 75 male participants for a total of 100 participants. In our sample in total, we have 60 individuals that self-reported that they deposited their recycles, and 40 individuals that said that they littered their recyclables. So not looking at gender at this point, just 60 people deposited, 40 people littered. Male participants are 75 out of 100 participants in the sample, aka 75% of the sample. So what would our expected value be? That's that value in red. If male participants represent 75% of the sample, we would expect them to represent 75% of all depositors and 75% of all litterers. So if we look at the deposit value, we observe 60 people depositing. 75% of 60 people depositing would be 45 male participants depositing. So again, if we are looking at what we would expect if we know nothing about anything. So we only know that males represent 75% of the sample. So our best guess would be that males represent 75% of those that deposit and 75% of those that litter. So 45 out of 60 depositors equals 70%. Similarly, 30 out of 40 litterers represents 75%. So those red values are our expected values. The black values, the black text, shows us what we actually observe. So we actually observed only 42 male participants depositing, and we saw a disproportionate number of male participants littering. Now, these differences are actually extremely small, so we would not expect them to be significant. But we can use this information to calculate whether what we observed was significantly different from what we would expect. So to do this, we subtract our observed values minus our expected values and then take the square of that, and then we sum things together. In this case, we would be looking at, for males, it would be our observed value of 42 for depositing and our expected value of 45. So that would be 42 minus 45 equals -3 squared equals 6. And then we would do the same thing for the individuals that were male and littered, for individuals that were female participants and littered, and individuals that were female participants and deposited their recyclables. So this can become a little bit of a difficult computation, but that's why we have the SPSS analysis to help do this for us. For your exam, I will ask you, for example, potentially, a question about the formula for chi-square analysis. I'm never going to make you calculate it by hand. I think when you do it by hand, it might help you on your own to kind of understand how the analysis is being calculated, but I won't make you do it on your own. So let's step back again and look at what we're doing with the chi-square analysis. This is designed for categorical variables. So that means our variables are either nominal or ordinal. And we want to avoid using ordinal variables with a wide range, like 1 to 7. It's more appropriate for ordinal level variables. There's a scale of 1 to 5 or less than that. There is no independent and dependent variable in a chi-square analysis. Make sure you understand this. Always use the language of association. The chi-square analysis is testing whether there is an association between two variables, but it's not testing whether these variables are, like, variable 1 is influencing variable 2 or vice versa. If we're going to do a chi-square analysis, or any analysis for that matter, the first question that we have to ask is whether our data violate any assumptions of the test. So what are the assumptions of a chi-square analysis? One that we assume for chi-square analysis and virtually all other analyses that we do is the assumption of independent observations. This is a question or an assumption that we can only address at the research design stage. If we screw up the independent observation assumption, there's nothing that we can do with statistics to actually change that. Independent observations just means that for participant 1, their score on whether they littered or recycled did not actually influence whether participant 2 littered or recycled. The value that we see for person 1 is not influencing the value that we see for person 2. What would be an example of dependent observation? Let's say we were looking at whether somebody went to a coffee shop and ordered a scone. We might find that individuals at 9 a.m. were more likely to order scones than individuals at 5 p.m. But maybe it's not because the individual at 9 a.m. differed from the individual at 5 p.m. Maybe the earlier individuals, by ordering a scone, actually reduced the number of scones that the coffee shop could actually sell. So by 5 p.m., the individual who could have gone and ordered a scone, or maybe wanted to, was not able to because scones simply did not exist at that point. So these observations are not independent of one another. What the person at 9 a.m. did impacted what the person at 5 p.m. could do. The most important assumption of chi-square analysis is that we have no cell with less than 5 expected observations. Very importantly, not observed observations. So for the expected count assumption, let's go back to that initial example of gender and recycling. If only 4 male participants deposited their recyclables, that's not a violation of the assumption. The assumption is that the expected observations cannot be under 5. This is a matter of sample size. So I'll give you a hypothetical example. If we had a sample size of 10 and there were 4 male participants and 6 female participants, and we're looking at recycling of yes, they did recycle or no, they littered, the expected count for males on littering and expected count for males on recycling would be less than 5 because the total sample is less than 5. We would have an expected count of, let's say, 2 for recycling and an expected count of 2 for littering. So we need to make sure that our sample size is sufficient. I'll do an actual example using the Pathways to Desistance Study data. So we might ask whether gang membership is associated with gun carrying. So notice I'm not saying are gang members more likely to carry guns than non-gang members. I'm leaving this an open-ended hypothesis. So what you're going to do for the chi-square analysis is you'll go up to Analyze, then you'll hit Descriptive Statistics, and then you'll move over to Crosstabs. And that's going to open up a crosstab box where you can enter your variables into the row box and another variable into the column box. Which one you select is not extremely important for the interpretation, but it can help just with kind of visualizing things. I always like to put in my hypothesized independent variable into the row box and the hypothesized dependent variable into the column box. Garson says the opposite, but I disagree because when we create tables in our Word documents, we typically put our independent variables in the rows and our dependent variable in the columns. Now remember, I'm using the terms independent or dependent variables simply theoretically. When it comes to the chi-square analysis itself, we're just looking at the association. We're not looking at whether one variable influences another variable. So here I have in my row my gang involvement variable, and in the column I have my gun carrying variable. Then what I'm going to want to do is go to the statistics box. And I want to click a few things. I'm going to click chi-square so that it will give me the chi-square statistic, and then phi and Kramer's v, which give me measures of effect size, and I'll explain what these effect sizes represent later, but for now just know that this is a box that you're going to want to click on. Then you'll also want to go into the cell box that you see in SPSS, and you're going to make sure that you click row and column. This is going to give you the percent of individuals that are gang members that carried a gun, but also the percent of gun carriers that were gang members. What I'm showing here is the SPSS output that you will see when you run a chi-square analysis. So at the top of the slide here, you'll see a cross tabulation of on the row gang involvement, and then you can see no and yes, and on the column ever carried a gun, and you can see no and yes. So how do you read this table? So if you look at gang involvement, you can see no and yes, and if you look all the way over to the right, you can see total. So you can see that there were 1,031 individuals that were never gang involved and 315 individuals that were at some point gang involved. Same thing with carrying a gun. If you look under no and then go down to total, 713 said no to carrying a gun, 633 said yes to carrying a gun. So our interest is in what percent of gang members carried a gun versus what percent of non-gang members carried a gun. If we look at the gang member column and yes, and then look at gun carrying and yes, we can see that 241 gang members carried a gun, which represents 76.5% of all gang members. That's 241 divided by 315. So look at how many non-gang members ever carried a gun. If we move our eyes straight up, we can see 392 gang members have ever carried a gun. 392 out of 1,031 non-gang members represents 38% of all non-gang members. When I'm interpreting a chi-square analysis, I'm almost always interested in the percent within the row. That is the percent within the independent variable. And here's why. Let's say if we looked at this table and we looked at percent within the column, aka percent within gun carry, we would see that 61.9% of all gun carriers were not gang involved. And I think this isn't very helpful or useful information unless we were also reporting on the percent of the whole sample that were non-gang members to begin with. So if we look at that, we see that 1,000 out of 1,300 participants were non-gang members, which means like close to 90% of the sample were non-gang members. So 61% observed versus about 90% expected is a significant difference. That requires you explaining a lot of additional details to readers. If we look at the percent within row, we're looking at, okay, among gang members, how many individuals carried a gun? And then among non-gang members, how many individuals carried a gun? And we can see it's almost a 2-to-1 ratio where gang members, 76% carried a gun compared to only 38% of non-gang members. So that's telling us what's going on. The biggest mistake that I see students make when looking at chi-square analyses is they'll report that there was a significant association between gun carrying and gang membership, and then they stop. You need to go at least one step further, which means interpreting whether gang members were more or less likely to be gun carriers compared to non-gang members. So was this relationship significant? To understand that, we have to look at the chi-square test. And what we'll be interpreting here is the Pearson chi-square. And if you look at that little A subscript, it says 0 cells have expected counts less than 5. So that means that you know that you've passed the assumption of no expected counts less than 5. Our chi-square value is about 143 and degrees of freedom equal 1. So we would do chi-square bracket 1 end bracket equals 143.46, which is our chi-square value, comma, p less than 0.001. And remember, this is now you're seeing an example of what I talked about earlier. That 0.000 value, it's not a possible value. We can't be 100% sure about a probability. Instead of putting equals 0.000, I put p less than 0.001. Then we have our value of phi. And our value of phi is giving us an indication of the strength or the magnitude of the association. And phi is represented by that little, I don't even know how to describe, a squiggly line that kind of looks like a P with another, or like a pitchfork or something like that. Our value of phi is just the square root of chi-squared divided by n. So we could actually calculate this if we wanted to. Our chi-square value was 143.46. If we divided it by 1346, we would, and then took the square root of that, we would get 0.326. So that's all that phi is measuring. And again, I'll talk a little bit more about how to interpret phi, how to interpret Cramer's phi later on in the class, but I don't want to deal with effect sizes just yet. I opened the class with just an example of an independent samples t-test where we looked at male participant and female participant differences across age at baseline, but now we'll go into a more interesting example. So here's the formula for an independent sample t-test. At the top, you see a mean. So whenever you see x bar, that means mean. An independent sample t-test is a test of a difference in average score across two groups. So x bar 1 is the mean value for one group, and we're subtracting it from the mean value for a second group. Then we're going to divide that by the square root of the standard deviation for group 1 divided by the sample size for group 1 plus the standard deviation for group 2 divided by the sample size for group 2. Again, not something that I'll ask you to hand calculate, but just letting you know what's going on with this type of analysis. To summarize, an independent sample t-test is just a comparison of means for two independent groups. Independent group means that a person's status in group 1 didn't dictate somebody else's status in group 2. A dependent t-test, also known as a paired samples t-test, what would a dependent t-test or a paired sample t-test actually look like? In this case, the paired sample t-test is not looking at a difference between group 1 and group 2. It's more like looking at a difference between an individual at time 1 and time 2. So let's say we took a sample of 50 individuals and we wanted to see whether exposure therapy helped cure somebody's degree of arachnophobia. So we could measure their degree of arachnophobia. Let's say it's a scale from 0 to 100, an interval level variable. We measured it from 0 to 100 for all individuals before experiencing intervention, so we'll call it time 1. And then we give them the intervention, and then we reassess their degree of arachnophobia at time 2. We would then be looking, instead of the mean between two groups, we'd be looking at the mean for the sample at time 1, and then the mean for the sample again at time 2, to see if we saw a change in somebody's degree of arachnophobia. Our null hypothesis with an independent samples t-test is that our means are equal, that there are no differences in average score between these two groups. We have the independence of a cases assumption, but we also have an assumption that our dependent variable is normally distributed in both populations. By both populations, I mean both groups. So it's not just running a univariate check to see if our age variable is normally distributed. We want to check to see if age is normally distributed amongst male participants and whether age is normally distributed amongst female participants as well. This is something that we do before we run the t-test, and I'll show you how we do this check later on. But just so you know, it's something that we do before the test. We also have a question about homoscedasticity. This is called Levine's test of equal variance. What this means is that the spread of the data of age is similar between male participants and female participants. And this is something that SPSS will calculate for you when you run the t-test. So how do we calculate or conduct the t-test in SPSS? Remember, first, before we run the analysis, we would need to check for that assumption about normal distribution within each group, but I'm going to show this later on. For now, I just want to focus on the test. We would go up to compare means, and we would hit independent samples t-test. Then we have to put our independent variable into the grouping variable category, and our dependent variable into the test variable category. I'm using these independent and dependent variable terms just conceptually. Our t-test isn't actually looking at whether our independent variable influences our dependent variable. So in this case, I'm going to look at whether gang members and non-gang members differed in their average level of frequency of offending in the last year, again using the Pathways to Desistance Study dataset. When we are looking at data in SPSS and when we have gang members and non-gang members, it's not that I'm writing into each cell in SPSS gang member or non-gang member. I'm using a specific numerical value to let non-gang member equal 0 and gang member equal 1. So in group 1 and group 2 boxes, I have to tell SPSS what the values are of my two groups. So if I want group 1 to be non-gang members, I enter a 0. I want group 2 to be gang members, so I enter a 1. It'd be the exact same thing if you're looking at male participants and female participants. If male participants equaled 1 and you wanted them to be group 1, enter a 1. You would also enter group 1 as 2 for female participants if you wanted female participants to be group 1. It really doesn't matter. It just is about how it would calculate the difference. It would either look at male participant average minus female participant average, or reversed, female participant average minus male participant average. And we have two key boxes that we want to interpret when looking at the SPSS output. So at the top you can see gang member status as no or yes, and the sample size, and then the mean. And this shows us the mean number of offenses in the past year for non-gang members and for gang members. So we can see that gang members averaged more offenses compared to non-gang members. Then the question becomes, well, is this actually significantly different? The first thing that we have to do is interpret the Levine's test for equal variance. Is the spread of data of frequency of offending similar amongst gang members compared to non-gang members? So we want to see whether it's significant or not at p less than 0.05. If it's non-significant, we want it to be non-significant. That means that we have equal variance assumed. That means we would interpret the top row of this t-test box. If p is less than 0.05, it means equal variance is not assumed, and we would interpret the bottom of that t-test box. In this case, we do not have equal variance. We reject the null hypothesis, which means we have to interpret that second row. And here's how we would write out this information. So what we would say is that we, just like chi-square analysis, we put t bracket degrees of freedom, and you can see on the slide here that the degrees of freedom is 416. So we write 416 point blah blah, end bracket equals our t value of negative 3.77, p less than 0.001. Once again, remember to interpret. It's not just that you found a significant mean difference. Interpret the nature of the difference. You say that gang members average a significantly greater number of offenses in the past year compared to non-gang members. One of the limitations of t-tests is that, as you saw in that box, you can only specify two groups. What if we wanted to compare frequency of offending across three groups of individuals that self-reported their ethnicity is either black, Hispanic, or white? So you could technically run three t-tests. You could compare black participants to white participants, black participants to Hispanic participants, and then a third test comparing Hispanic participants to white participants. Issue with this approach is now we're running an unnecessary number of tests. We're running three tests for one question. What does that do? It inflates our likelihood of a false positive, that type 1 error. We want to answer this question with a single analysis. And so the solution to that is to do an ANOVA, or an analysis of variance. An ANOVA is the exact same logic of a t-test, we're just adding a different group. So we're looking at whether the mean for group 1 differs from group 2 and group 3, and whether the mean of group 2 differs from the mean of group 3. We also have similar assumptions to the t-test about the normal distribution being true for group 1 and group 2 and group 3. Not just that the variable that we're looking at, let's say it's offense frequency again, not just that offense frequency is normally distributed for the sample, but that it's normally distributed across the three groups. So here you can see that each group has a normal distribution. The other aspect, or the other assumption that we'll be making, is that Levine's test continues to not be violated. A nice clear tutorial is provided in the link here. Basically, here we're just asking whether the average frequency of offending differs across the three groups. And we're asking, what is the probability that the differences observed between means is just due to chance alone? For the hypothesis test, our null hypothesis is just U1, that just means the mean for group 1 is equal to the mean for group 2. The mean for group 2 is equal to the mean for group 3. The mean for group 3 is equal to some other mean for some other group. Our research hypothesis is not going to be that group 1's mean is significantly higher than group 2's mean. Our research hypothesis is going to be that among the groups there are some mean differences somewhere. We're not specifying where they are or whether it's higher or lower. Here is our research questions. Do mean levels of self-report offending differ across ethnicity? So I've written out the null and research hypotheses. Don't feel like you need to do these in your term paper. You can do them maybe informally, but when it comes down to like empirical papers in criminology, we don't often see formal hypothesis testing because often we're doing more exploratory research where we're not making real clear hypotheses. We're just trying to inspect our data. So it's very straightforward for the analysis in SPSS. Mash that Analyze button, go to Compare Means, and then you're going down to that one-way ANOVA. In the dependent list, we will enter our interval level variable, so that's going to be frequency of offending. And then in our grouping variable, we're going to enter our ethnicity variable. And then we don't actually have to specify like who is group 1, who is group 2, who is group 3, and so on. SPSS just figures that all out for us. What you'll want to do once you've done this is you have to enter the post hoc little tab and select which type of post hoc test you're going to do for each type of scenario. The two scenarios being equal variance is assumed or equal variance is not assumed. So the post hoc test is so important. For the t-test, we are interested in whether group 1 differs from group 2. There are no other possibilities other than that. With ANOVA, there are multiple possibilities. Group 1 could differ from group 2, but group 2 could differ from group 3. Group 3 could differ from group 1, and so on. What we want to do is, once we've identified whether there's a general difference in means, we want to understand where this difference actually comes from. Is the significant difference between group 1 and group 2, or between group 1 and 3? And that is where the post hoc analysis comes in. And we interpret different post hoc analyses depending on whether equal variance is assumed or not assumed. I select Bonferroni for equal variance assumed and Tamhani for equal variance not assumed because these are both conservative tests that reduce the likelihood of type 1 error. We also want to go into that options box. I have no idea why ANOVA makes you do this because they do it automatically for t-tests. We want to hit that descriptives button. That's going to tell us the average score on offending frequency for each grouping variable. The homogeneity of variance test we have to select so that Levine's test will run so we can assess the null hypothesis that the variance or the spread of the data are the same within each group of our independent variable. In this case, it's ethnicity. Here are the key output that we'll begin to look at for the SPSS ANOVA output. So at the top, you can see the average frequency of offending within each ethnic group, but it doesn't tell us whether these are significantly different. We want to first, before we interpret whether ANOVA is significant, look at the homogeneity of variance test, which we see that we have violated. We are rejecting the null hypothesis here. Equal variance is not met. So when we interpret our ANOVA analysis and when we interpret our post hoc tests, we're going to be interpreting things with this failure of Levine's test in mind. I'll talk later about what we would interpret if we violated Levine's test, but for here, let's just pretend we passed Levine's test. So equal variance was assumed. What we're interested in here is whether our value of f is significant. So we can see our f value, our f statistic is 3.28, and it's significant at p less than 0.05. Specifically, the value associated with the f statistic is 0.038. So we know that there are significant differences in the frequency of offending amongst ethnic groups, but we don't know where that difference exists. For that, we have to interpret the post hoc comparison test. We would either be interpreting Bonferroni if equal variance was assumed, or Tamhani if equal variance was not assumed. What we're looking for here is we've got at the top, let's start with Bonferroni, we have the group of interest being white, and it's compared to black and compared to Hispanic. What we're looking for are the little stars. The stars tell us which of the comparisons were actually significant. So you can see that white participants were not significantly different compared to black participants and compared to Hispanic participants. Where the differences existed was when we compared black participants to Hispanic participants. That's the only difference that we see here. What is the nature of the difference? Well, one of the things that we could do is flip back to the initial descriptives and it would tell us the mean for black participants and the mean for Hispanic participant, then we know which one is larger or smaller. What we can also do is just look at the value in the mean difference column where it says I minus j. I is the first column that we see in the Bonferroni little table. So white would be at the top there, white equals I, black equals j. The mean for white minus the mean for black equals negative 35.88. So in this case, if we're looking at the mean for black minus the mean for Hispanic, it's showing that black participants average 60.5 or 60.60 more convictions compared to Hispanic participants. This isn't saying that black participants average 60 convictions or 60 offenses. It's saying that they average 60 more self-reported offenses compared to Hispanic participants. How would we report the results here? So let's say that we are assuming that we had equal variance assumed. We would do F, and then we do bracket 2 equals our degrees of freedom, comma 1283 equals our sample size, end bracket equals our F statistic, and then P equals 0.038. If we were interpreting equal variance as not assumed, meaning we're looking at the Tamhani post hoc procedure, we would then talk about where did these significant differences exist. So we would say that individuals that self-reported as black average significantly more self-reported offending behaviors, and then we could provide the mean, the standard deviation, compared to individuals that self-reported as Hispanic. Now you'll notice I put that P equals 0.022. I got this directly from the post hoc table that gives for each analysis an alpha value to show whether it was significant or not. Now we're on to correlations, which is another parametric test that assumes the normal distribution of both your variables. So there are two types of significant correlations we could see. A positive correlation, which means that when group 1 increases, it's associated with an increase in group 2, or vice versa. The key here is that there is no directionality. A correlation isn't looking at whether group 1 or variable 1 influences variable 2 or variable 2 influences variable 1. It's just looking at whether there is an association between those two. When one variable increases, the other variable also increases. That's a positive correlation. A negative correlation would be where one variable increases and the other one decreases. No correlation is where you would see no really uniform pattern across the data that we're looking at. So what are we actually looking at with these plots, these scatter graphs? What you're seeing is we would plot on the x-axis, that horizontal axis, we would plot the value for, we would look at values for one particular variable. Let's say we're looking at psychopathy and frequency of offending, where psychopathy is scored on an interval level scale and frequency of offending would be a ratio level variable. So let's say we usually would put our independent variable on the x-axis, so that would be psychopathy, and our y variable would be on the, or our dependent variable would be on the y-axis, so that would be self-report offending. For each individual in the sample, we would be looking at what is their psychopathy score, so we would plot that on the x-axis, and where did they score in terms of self-report offending. So if their psychopathy score was 30 and their level of offending was 300, then we would mark that plot, that dot, along the graph that we see here. So a correlation is looking at two continuous variables, whether they're interval or ratio, and sometimes you can get away with ordinal variables as well. The correlation is always between 0 and the absolute value of 1. So it could be perfectly negatively correlated, which would be -1, or perfectly positively correlated, which would be 1. We call this Pearson's correlation, or Pearson's R. R is a little subscript or symbol that we use to represent a correlation, and it's very sensitive to outliers. If we're looking, and we'll notice when we look at offending frequency, we'll see a lot of outliers. Some individuals have self-reported like 1,000 crimes. If we have this outlier problem, we can do Spearman's R. What this does is it rank orders our interval level data, or it will use ordinal level data, which is inherently rank ordered. One of the assumptions of a correlation analysis is that it assumes linearity. What this means is that like a 1 unit increase in psychopathy is associated with a consistent increase in frequency of offending. Let's take psychopathy score, for example. If a person scores a 6 on, let's say, the PCLR, and we're comparing them to somebody with a 1 unit increase, so who scored a 7, the magnitude of the difference in offending that we see here should be the same as the magnitude of the difference in offending that we see when moving from somebody that scored 20 to somebody that scored 21, or someone that scored 30 to someone that scored 31. So the idea is that the relationship is the same across all values. To visualize this, you can go up to graphs in SPSS and do a scatter plot where you can plot your independent variable on the x-axis and your dependent variable on the y-axis. And what you're looking for is just a line that will either go like this or go like this. If you see a line that does kind of this quadratic shape where it curves towards the end, that's showing you that your data are not linear. So our formula for our correlation analysis is just y equals a plus bx. Our a value, or our alpha value, just represents our intercept. The intercept is our value of y when x equals 0. So what is alpha, or what is the intercept? The intercept is where along the y-axis we would find a dot when our value of x equals 0. Our value of b, or beta, is representing slope. What is the degree of increase in our y value when our x value increases by 1 unit? So when our independent variable moves by 1 unit, what is the magnitude of the increase in y? X in this equation just represents any given value that we might have in our data set. So let's do an actual example. Is there a correlation between features of psychopathy and self-report offending? So to do a correlation analysis, we just do a simple go up to Analyze, Correlate, and we're going to hit Bivariate. Then we're going to be looking at just entering our two variables into the variable box. You don't have to specify anything else, but you can look down at correlation coefficients and you can tell it to do Pearson, or if you want it to be rank ordered, you could specify Spearman. You also have that option of selecting a one-tailed test, but again, I really strongly advise against doing that. You should be focusing on a two-tailed test. So our correlation analysis gives us very clear information. It's so easy to interpret. What we can see is on our row column, we have frequency of offending. Below it, we have our total PCL score. So it doesn't matter, it gives you the exact same information. But I like starting with our independent variable, which is PCL score. So we can look at the Pearson correlation, and we can see the value is 0.277, and it's significant at p less than 0.001. We can see that by it being a positive value, we know that increases in features of psychopathy are associated with increases in offending. Let's say if we looked at Spearman correlations, if we check that little box in SPSS, it would tell us that the rank order score for the PCL was significantly correlated with the rank order for frequency of offending. You can see that the magnitude of the correlation coefficients are actually quite different. It's almost twice as high when we ran the Spearman correlation coefficient. What this means is that when we violate assumptions, such as outlier assumptions, we underestimate the correlation relationship. We had outliers in our data, specifically with offending frequency, and I'll show this to you later on. But because of these outliers, we've underestimated the degree of the correlation between psychopathy and offense frequency. So Spearman helps us correct for this by rank ordering everybody. And we can see that there's a fairly strong positive correlation between PCL score and offending. Sometimes I really like being able to visualize things. What visualization does is it shows us the general nature of the relationship, but it can also help us detect outliers and assess for linearity. If you go into the legacy dialogues, hit that scatter dot line, and if you double click on the graph that it shows, it will allow you to select add line at total or add fit line at total. If you were to see a curved line, that would suggest a nonlinear relationship. What this line shows is that as we move from left to right across the x-axis, the line also slopes upward. This means that there's a positive correlation going on. If you look at the top, you can see the r squared value, which is 0.077. Where did this value come from? It's actually just the correlation coefficient squared. So if you go back into our SPSS output, what you'll see is that the correlation coefficient for the Pearson correlation was 0.277. If we square that, we would get the r squared value, which represents the percent of variance explained in this relationship. So we've got about 8% of the variance explained. So here's how we would report that Pearson correlation. The general formula for reporting is we would put RDF equals the actual correlation coefficient, where the degrees of freedom equals n minus 2. What that means is our sample size minus 2 for the two variables that we included in the analysis. So in this case, we'd write up R, our degrees of freedom, 1,295, equals our correlation coefficient of 0.277. And in this case, it was at p less than 0.001. Then we would want to interpret. We would want to say that there's a significant and positive correlation between PCL score and the number of self-reported offenses. Notice that we're not saying anything about the direction of the relationship. Alright, so I know that was a lot, but I wanted to lay kind of the foundation of what each analysis does before we move on to interpreting effect sizes, which tell us about the magnitude of the relationship. So we just looked at correlation analyses. Is 0.277 actually large? Is it medium? Is it small? How do we know? What are some thresholds or standards or criteria that we can use so that we're not subjective? So that we don't have one person saying that a correlation coefficient of 0.500 is large and another person saying it's small. So we can actually develop some standardized ways of reporting. So I wanted to talk a little bit about effect sizes, and I'm not going to go into length. This is not an exhaustive description of effect sizes, but I want to cover them a little bit because I think we're witnessing a bit of a revolution in the social sciences, and criminology is a little bit behind in that we continue to focus almost exclusively on significance testing, which is informative of the probability that the results that we observe are based on chance or random probability from what we would expect from the population that we're sampling from. What effect size provides us is information about the strength of the relationship with the difference that we're observing. So we'll talk a little bit about a few effect size examples, including phi and Kramer's v, which are associated with chi-square analysis, and eta, which is associated with ANOVA, Cohen's d, which is associated with t-test, and Pearson's r, which obviously is associated with correlation coefficients that we just touched on. Phi and chi-square are ways of calculating proportional reduction in error. This tells us about the percent of variance accounted for in the association between two variables. For chi-square analysis, we're only focusing on two variables. So to calculate proportional reduction in error, we would just square the value of phi. And we've seen this in the chi-square example where you have phi and you have Kramer's v. What's the difference between phi and Kramer's v? Phi is calculated when you have at least one measure with only two categories. So you have two variables in your chi-square analysis. If at least one of those variables is dichotomous, then you would interpret phi. Kramer's v and phi are the exact same, except Kramer's v is when you do not have one of your two variables being dichotomous. So it's a different formula that penalizes the additional degrees of freedom that are found when you have two variables and maybe they're both measured on a scale of 3 or something like that, or they're ordinal variables on a Likert scale from 1 to 5. Next, we'll talk about Cohen's d, and this one's more important to talk about because SPSS will not calculate Cohen's d for you. The Cohen's d is associated with t-test, and there's a four-step process for calculating Cohen's d. Step 1 begins with calculating the mean difference between two variables. So I've got age of male participants, 16.05. Mean age of female participants is 15.99 for a difference of 0.06. Then we calculate in step 2 the pooled standard deviation. What is this? We just take the standard deviation for males and square it, and then we add to it the standard deviation for female participants squared and divided by 2, which gives us our value of 1.21. We squared there, so now we're going to calculate the square root to return to our original unit of measurement. So square root of 1.21 is 1.10. Fourth and final step is to divide our mean difference value that we got in step 1 with our pooled standard deviation value that we got in step 3. 0.06 divided by 1.10 equals our 0.05 Cohen's d value. I am going to upload to Canvas, remind me if I don't, a simple Excel spreadsheet that will allow you to plug in your values, and it will calculate the square root of your pooled standard deviation and everything like that for you. So all you need to do is enter the mean and standard deviation of both your variables, and that will actually give you your Cohen's d value. The bigger question is, what does Cohen's d even mean? What is this telling us? What it's telling us is the size of the differences between our two categories of interest, so male participants, female participants. What we're doing when we're doing steps 2 to 3 is calculating the standard deviation, which is basically telling us how much variability is there within our two groups to make us less confident in the differences between the two means. So let's say our average age for male participants was 16.05, but our standard deviation was 10. What that's telling us is that 68% of our sample of male participants are somewhere between like 6 years old and 26 years old. So that's not a very homogeneous group. And so when we're comparing this group to women, then we're not really sure, like, is this an actual difference? So calculating the standard deviation pooled square root is basically giving us a penalty to our calculation of mean differences. So we're weighting the strength of our differences in step 1 versus the penalty that we calculated in steps 2 to 3. What is a meaningful Cohen's d value? So these are the Cohen's d benchmarks developed by Cohen in 1988. It's very simple. Just type into Google Cohen bracket 1988 end bracket, and you'll probably find the empirical article for these benchmarks. We're basically saying that a small effect size is one where the Cohen's d value ranges between 0.20 and 0.49, and you can see the rest of the interpretations of effect sizes in this particular slide. So this is how you can interpret the magnitude of your t-test. What is Cohen's d actually representing? Essentially, it represents the number of standard deviations by which the two groups' means differ. So it's not about the standard deviation of group 1 and the standard deviation of group 2. It's about how many standard deviations apart is the mean difference between group 1 and the mean difference between group 2. If you're interested, here's a link to just an interactive website that can help you take a look at different ways of expressing Cohen's d. Correlation coefficients are innately a natural effect size. Like Cohen has provided benchmarks for correlation coefficients. I believe Garson will talk about them as well. And so you can see up here, if you want to interpret the strength of your correlation coefficient, here are some of the ranges that you can use. Unlike Cohen's d, correlation coefficients cannot exceed 1. If you take the squared value of your correlation coefficient, you get the percent of variance explained, just like proportional reduction in error. So proportional reduction in error and correlation coefficients squared are actually telling us the exact same thing, just with respect to different types of analyses. Chi-square analysis is an association between categorical variables. We can see proportional variance explained there. Correlation coefficients are looking at proportional variance explained with an interval level variable or a ratio level variable. What I'm going to get into next is a bit of like the ugly truth behind research that's done. In criminology, we almost constantly violate assumptions about normality. So when you think about first step in the t-test, which is to check to see if, let's say, frequency of offending is normally distributed within group 1, which might be gang members, and group 2, which might be gang members. This is almost always violated. And the reason why people don't talk about it as much is usually because this violation doesn't matter, because of sample size is large enough to overcome the limitations of violating such assumptions. For this class, I'm always going to want you to show me that you understand the assumption, show me that you can calculate or test for the assumption. I'm not so concerned about whether the assumption is actually violated. I just want to know that you know what is going on. That will kind of bring us to week 3's material.